I want to thank everyone for coming to join us for the NAIR Pilot Partner Series that we've got going on. We are very excited to have our next Pilot Partner Series with Lexset. We will be having a 45-minute presentation with about 10 to 15 minutes of Q&A at the end. So if you have any questions during the presentation, please submit via the Q&A button here on Zoom, and all of the questions will be answered at the end of the presentation. This session is going to be recorded, so if you'd like to go back and rewatch, the video should be posted to the NAIR Pilot YouTube channel within the next 2 weeks. And we will go ahead and switch over to our presenters. If you'd like to introduce yourselves, and feel free to start whenever you'd like.
Okay, excellent. Let me share my screen and I'll introduce myself. So, hi, my name is Francis Pitanti. I am one of the co-founders at Lexset. Yep, I turned off my video, trying to share my screen. Let me just share my screen so I can focus on talking. Okay, and bear with me. Okay, is my screen sharing? Yep, thumbs up.
Yes, good.
Yes.
Oh, okay, great. So I'll try again. I'll introduce myself. My name is Francis Pitanti. I'm one of the co-founders here at Lexset. I am the CEO and also the CTO. So I'll be giving a bit of I'll have the CTO hat on here. I'll give more of a little bit of a technical rundown. And we're joined with Christian Gartland, who I will let him give a little more detail on himself and say hi. But he is one of our kind of lead engineers. He's been with us a long time, and he'll be running the software demo after I go through a few slides, and you'll be in very good hands. He helped us build much of what he's showing. So, Christian, you want to just say hi quickly?
Yeah, hi everyone, Christian Gartland here. Full stack engineer at Lexset. Been in the company for about 5 years now, and yeah, we'll be doing a demo later. Excited.
Great, awesome. So let's jump in here and let's talk a little bit about, I guess, about what Lexset is, what we do. And I think what we're really focused on is how we can leverage, simulation, or, as we'll talk more broadly, synthetic data. That's becoming a kind of a wider topic. Is like really looking at how we can leverage these simulation technologies to improve AI. And there's a number of values to these kind of methodologies that we'll go over as we work through this presentation here. Um, and we have two products. We have our flagship product, which is Seahaven, which will be the focus of today's conversation, and the demonstration. But we also have another product that we call Oceania, which is a kind of I guess, how we put some of that synthetic data to use. We have a kind of an image analytics pipeline, where we can leverage synthetic data in a variety of ways to train models, to extract insights from images. We've applied these simulation technologies to everything from, fine tuning visual VLLMs to simple convolutional networks, and we'll go through some examples of how those get used. But the focus of today's talk will be on Seahaven, which is our kind of flagship product. It's the product that we use to synthesize synthetic data, and it's used by customers in the government as well as Fortune 500 companies. It's been evolving. It's been around about as long as, maybe even longer than Christian's been here at the company with us. So how does Seahaven work? So there's a couple components, I think, to the platform and how all this comes together. Macro level, the problem we're solving with Seahaven is that most simulation technologies are built for studying a single phenomenon, right? Or like how some sort of particular configurations of settings work. Where they tend to fall short is when I want to study like a whole domain, right? I want to kind of set wide boundary conditions, and I want to collect a lot of data that's representative of maybe like a kind of like slice of life or slice of parameter space. And Seahaven's our way to address that. We think simulation for AI has a unique set of constraints, and what I just said being one of them. We're often interested in modeling kind of behaviors. We're interested in modeling a domain. We're interested in modeling what is possible. We're not typically interested in, there are exceptions to this, but focusing in really closely on some kind of micro use case. So again, we're kind of looking to paint with a broader brush here. Seahaven is built as a kind of physics-based 3D simulation environment. We do have some kind of solutions and hybrid pipelines that I'll talk about a little bit later, where we do leverage generative AI, specifically diffusion models, in order to augment this process. So it starts by loading in 3D content. So you'll see this in the demonstration, but we load in 3D assets. These can be built by an engineer or a 3D artist. And Lexset also offers a large database of different models that would be common objects. I guess this is literally the name of the data set. So the COCO data set, common objects in context, things like trees, cars, houses, assets to help you build your environment. And often, we'll build custom, or customers will bring 3D content for specific things they're looking to introduce into the simulations. For example, maybe a specific model vehicle, a specific kind of geospecific location. We can bring in import 3D assets like that. We're compatible with a variety of different 3D formats to do that. The scene creation is kind of, I think, where a lot of the power comes from here and the magic of it all. Again, like I said, we're going to be trying to orchestrate, and create thousands or hundreds of different types of scenes. For example, if we're trying to model a highway or any busy street, right? We don't want just one busy street. We want to procedurally build hundreds or thousands of those, each with their own unique configuration, maybe unique position of the sensor or configuration of that sensor, different lighting, different times of day. And we'll go through that in the demonstration, but you'll see exactly how we configure that. Additionally, we're going to see mostly electro-optical or kind of like color RGB images today. We also can simulate a variety of different types of sensor modalities. We do LiDAR, sonar, radar. We're building a thermal capability. We have a capability for simulating synthetic aperture radar. I'll show a little bit of that output later in the slides. And then most of what I'll talk about today is on the analytics side. Domain gap is a big deal here. And that's how different your simulation is from your ground truth. And, really nailing down what's right for your project. Kind of how you tackle domain gap really depends on what kind of data you might already have. What's your model architecture like? So we provide a lot of tools as well as, services as a company to help people really kind of fine tune and get the right simulation configuration to address any issues with domain gap. We'll get into that in a little more detail. Why use synthetic data at all? So there's a couple of reasons for this. One, some of the more obvious ones you'll see here up at the top. Sometimes you just don't have the data. It's scarce. It's costly, right? It may have certain sensitivities. People's privacy, is important. We do a lot of work with the government. Maybe data is classified, for example, and you don't have access to it or you can't easily share it. And on the other end of this, I think aside from some of these obvious things is edge cases are hard to collect, even if you have a lot of data. And often edge cases can be some of the most critical and crucial data points to train against, especially in use cases where you're dealing with like autonomy, whether it's like robotics or vehicles of some kind. And then, I think I'll get into here, you can also help improve generalization of models, through kind of like feature level engineering, and we'll give some examples of that. Having synthetic data, I think, allows you to kind of architect your signal, and it helps you kind of introduce or manipulate, the data set that you might have, to kind of modify that distribution and modify what the model might be learning. And if you're smart about that and you kind of leverage some of the analytical capabilities that we have, that can be a very powerful aspect that I think is often overlooked when it comes to synthetic data. I think we focus a lot more on, just getting access to data you may not have. But regardless, it's a very powerful tool when it comes to really kind of maybe getting over the line, getting those kind of last kind of points of accuracy that you might need to get. And I have a few examples of that. So the workflow generally, for those of you listening who may already be developing or have a lot of experience with AI, um, so first but you're not using synthetic data today. Start by defining your parameters of your virtual world. Like what does the simulation look like? What are the things I want to manipulate? What are the parameters I want to manipulate? What are the boundaries of my simulation? What are the kind of limitations of that? We have a no code interface that will walk you through that shows you how to kind of set that simulation up or those boundaries up. We then run, like I said, hundreds, thousands, however many you need of unique simulations to generate unique data points. We export and aggregate that data for you so you can start training right away. And this graph is probably not exactly a loop, but we very much see this as a loop. This is a process, that you can continue to adapt and refine your model even after it's been deployed in the world. You can use these techniques to help adjust with things like maybe like kind of domain drift and things like that as you need to improve your model. And just to circle back on that point I made earlier, I think really if you want to kind of come to synthetic data with the right mindset, I think it's important to understand that this is data that you can design, and I think it's artificially generated, and it's something that we can set it up to be a perfect mirror of our own world, but we can also set it up to deviate from that, whether those are edge conditions or, like I said, maybe you're trying to introduce features into a data set to help your model learn certain concepts. But again, this is not necessarily about discovery so much as it is, kind of designing what your data set needs to look like. We see it very much as like a kind of an operative tool that you can use to improve your model, and get into some very fine grained kind of optimizations, and improve your model in some unique and targeted ways. So synthetic data, it's evolved a lot over the years, and again, I'm speaking to all of this through the perspective of a kind of visual data. So we work exclusively on computer vision. So this is in regards to kind of vision based data. So simulation was really, we started as a simulation company. We started producing procedurally generated 3D scenes. That's still really the core of our work. We do a lot of work in different kind of sensors where there's a lot of reasons, I think, to use procedural and physics-based simulation over generative AI right now. There are some advantages to generative AI, which I'll show here on the next slide. Particularly, we think sort of through a hybrid or combined approach. But the physics-based simulation gives you a kind of at least a truth to start from, and a level of control that right now we find kind of difficult. At least if you want to really get, I think, some of the kind of real benefits out of synthetic data. So let's just kind of a quick example of how we might use these things together. So in a case like this was a project we did, looking at manufacturing defects, and the alignment here of these bolts, right? For example, like this is how they might check if the bolts are kind of torqued out of alignment. What we did in this case was, because the generative models were really quite good at generating some of the fine details, and you'll hear me kind of talk about this a lot as like kind of high frequency space. So maybe like if we're talking like high frequency things like texture, maybe as we get a little further in this talk, we'll talk about things like noise and various types of compression artifacts, for example. Diffusion models can be very good at kind of enhancing the realism there. However, where we find they often fall is if I need, specific image compositions. I need to model, the behavior of certain mechanical parts and how they're interacting. It can be very difficult to teach diffusion models these types of mechanics, and sometimes, the amount of effort just exceeds the value you're getting out of it. But what we find is, like, by taking a hybrid approach, we can generate kind of kind of like control data, almost using diffusion models in the way you might use a ray tracer to fill in fine details. And we find this is like a very, very good kind of approach for kind of hybrid pipelines. For things like, radar, lidar, sonar, we would probably stick to simulation. But I do want to talk about how this kind of these workflows are evolving and changing a bit. Just a little bit more detail on that project, right? So you'll see here what we're actually generating with the simulation pipeline. You'll see those colored images, right? This allows us to kind of model and vary, how those bolts might torque or change. We can then send that colored information, that kind of semantic information, and depth information and surface information into the diffusion model, and then generate, as you can see, highly realistic imagery that would kind of align to the parameters of that simulation. So it's just an example of how a hybrid approach may be really effective. And what I'm going to talk now a little bit about is like, what kinds of new capabilities, can this unlock? There's a lot of different ways, because we have this, once a simulation is built, right, we have an ability kind of just like we're changing the skyline here, right? We're just changing the orientation of that bolt. We're able to produce a lot of different variations of things, and whether those are variations in how they're observed, right? So like, like I said, lighting, camera position, or we can also manipulate the environment as well and produce different types of edge cases. So I like this example because it's a nice, simple example, and it gives a very clear kind of, I think, I guess, transformation to how the model's processing the data as a result of the synthetic data. So up above, you'll see two images. The one on the right is synthetic. The one on the left is real. These are from an open source data set called MSTAR. It's a SAR data set, and these are looking at different kind of vehicles on the ground. And what you'll see here in each of these, the first one, as you go down the page, these are activations from a classifier. So what we're trying to do is classify different targets on the ground. Initially, this data set's quite small. You'll get about like 200, 500 images on the high side per category. And what you'll notice is the model, because the data set's quite limited, right? It's starting to index on features in the background. This was a data set where all the kind of objects of interest were in the center of the frame. And over time, what you'll see are these like activations in the upper right corner that were kind of caught, leading to some confusion, right? Whether this was some kind of a persistent artifact on the ground from when the data was collected, or maybe there's just something about the noise that we're getting from the SAR sensor. But regardless, it wasn't really accounting for the key feature, like the features that we wanted it to, the features from the actual target in the center of the frame. So what we were able to do is introduce some added distribution noise into the background, effectively kind of showing the model like that, hey, like, look, there's not a lot of structure here. If you want to succeed in classifying these images, let's focus on features that are actually around this target in the center of the frame. And if you look at the last chart here at the bottom, you'll see, the strongest activations are in and around the target, right? They're kind of on the body of the vehicle, the shadow. And I think this is a really kind of good example where going out, collecting synthetic aperture radar data to correct this issue at a really large scale is most likely probably not going to be an option. We were able to see a kind of clear issue as we were interrogating the model. And then we were able to kind of introduce a new signal into that data set, as well as expanding it, right, by just kind of domain matching perfectly and expanding the data we had. But really kind of clearly and scalpel-like address an issue with the model that improves the performance and the reliability of that model. So, just to kind of go back to kind of workflows and how do you think about this in your own work? In this particular case, just using this as an example, first step was we noticed that the model wasn't performing really to I think to what we were expecting or hoping it would. We looked at a variety of different things in the model. We started to see some strange behaviors in the activations, so we analyzed the activations. We noticed those activations were not really aligned with the target. We also went on and performed some domain matching exercises, which I'll talk about in a little bit about how we do that. We found that really, I think the issue was there were some persistent features in the background that do not really mimic reality. And we needed to kind of expand variation and diversity there in the backgrounds. So we introduced this out of distribution noise as one possible technique, which worked quite well. Um, and then again, you can keep iterating on your synthetic data like this, but the idea is that you're able to kind of react quickly. So you can examine your model, you can come up with a plan of action, adjust data, introduce new data points, try to fix the issue, and iterate quickly, which is really something we try to really focus on. Fast iteration is really important when you're developing AI models. You don't want to wait months to go collect new data, or maybe it's not even possible. So let's drill in a little bit more into the domain matching technology. The way we look at this is we kind of look at the different scales, right? I talked earlier about frequency space. So what we'll try to do is, we'll look at the kind of smallest levels, and we have a Python package, and maybe Christian, when you give the demo, you could show just a little bit where that is in the documentation. But we have a Python package that will allow us to analyze things at kind of like high frequency level, right? Things like at the pixel level, maybe distributions of color intensity, compression artifacts, noise signatures, things that are kind of, maybe have like a kind of a small kind of neighborhood around them, or maybe are confined to a single pixel. The next level would be like how's the scene composition looking? A lot of our customers are doing work with object detection, so they're trying to localize things in frame. This can be really important there, right? Are we placing things as the relationship of the sensor to the object of interest? Is that coherent, and is that aligned with real world conditions, how that sensor tends to behave? And then lastly is actually using the AI models to inspect this, right? Looking at the generating embeddings from your model, comparing that to how the embeddings look for the synthetic data, you know, depending on how your model is trained, and like we saw earlier, they're extracting different types of features, right, in order to make categorizations. So we're kind of looking at that in the embedding space as well, and trying to reverse engineer into changes we may need to make in the data set. So kind of using all of these tools together, we're able to interrogate the synthetic data, and then either align it with the real data perfectly, or maybe we want to drift a little bit outside of the data we have. Maybe the data we have is too limited. But this gives us the control, and it gives us the ability to measure. Before I turn it over to Christian to do just a couple of just to do a demonstration, I want to go through quickly just a couple of use cases and examples. These are some of the more popular use cases, but running this company for a while now, we've seen really all kinds of applications for this technology. Some of which may be around like aerial imagery, right? So looking at kind of imagery from drone or satellites, things like forest fires, maybe kind of tracking smaller objects on the ground. There ISR applications. There's all kinds of things that we've kind of seen here. Assembly, making sure things are kind of assembled properly. It's kind of along the lines with manufacturing. We've also seen a lot of applications for manufacturing where highly precise manufacturing methods. For example, like maybe you're making electronics or semiconductors where failures are pretty rare. Synthetic data can be a really powerful tool in those situations for modeling those types of defects. And then another one that's important, and again, I think like in the spirit of things that we don't talk about enough when it comes to simulation, algorithm verification. Um, I guess this is an example of a company. They wanted to detect different types of threats in people's backyards from a outdoor like infrared camera, right? So these are things that like their edge cases. They didn't have a lot of data. They maybe had enough data for training, maybe not enough data to do a full verification, especially different edge cases that could manifest. So we can use simulation to kind of help test algorithms as well. Um, And then lastly is in space operations. Space is another place where not a lot of data makes it back to Earth. Can be kind of slow and expensive to send data back, especially from like in orbit. So there's a real data scarcity problem when it comes to space operations and space autonomy. So we're able to use synthetic data there to generate that, and we have a product called Seahaven, which is specifically aligned for modeling in LEO and GEO orbit various kinds of behaviors. So again, we're not going to show that today in the demo, but if you have any questions about that, please feel free to ask. Christian, I'm going to stop sharing and I'll turn this over to you if I can figure out how. There we go. Okay.
Great. Yeah, I'll just share my screen here. Great. Thanks, Francis. Yeah, so this is Seahaven. This is our graphical user interface, where you're able to configure, submit, and manage your synthetic data simulations. And just before I get started with kind of going over our sample simulation here, I'll just show some output, so you have an expectation of what the data will look like, and then explain how we're getting to this finalized image and what steps within the pipeline contribute to that. So in this example, I'm taking a series of drone images of a parking lot. That parking lot is populated with different vehicles and people, and it uses many different parts of our simulation pipeline to do that. And I'll get into more detail when we get to those parts. Furthermore, there's some vegetation that we're also randomly populating on the ground plane. So I guess it might help if I start with our simulation editor. So the simulation editor is the primary page where you'll be configuring your simulation, your 3D simulation. There's multiple different tabs here with different blocks. So each component in your simulation is defined by a block, the base of which is your workflow. So I'll start by dragging out our workflow, and I'll build up side by side what the simulation is, starting with the workflow block. Again, every simulation is required to have a workflow block. In terms of our other like offshoots of the platform, Seahaven, there might be a slightly different workflow block, but it is a workflow block nonetheless. So starting with, there's multiple different sections in the workflow block: scene, relationships, camera, etc. These are different modules which define different components, and in general, it's a sort of linear progression, starting from top going to the bottom, and this is the order in which all of these operations are executed. So you can think of starting at your scene components here, and then executing then to relationships, then to your camera, et cetera, et cetera. And then there are also some image output parameters here, which I will get to in a bit. Starting with the load 3D asset from collection. So that's defining our the base of our simulation here. Sorry. This is loading a static asset in our scene, and in this case, the collection is a collection of 3D assets. So land, scene, that's my collection that I'm loading a blend file from. And that establishes, I think in that scene, it's just the ground plane, not including any vegetation or any of the other assets. So I'll plug that into my scene here. And then in the variables, I can access a collection, which this collection is, it has all of the assets in your user account, and you can select from a dropdown from all the collections that you have. In this case, I'll just copy over the parking lot scene. The second part of my scene composition here is the environment. So I've loaded in geometry, however, there's no lighting currently here. So for the lighting system, I'm adding in a physical sun and sky. Another lighting option may be adding in HDRI lighting. Depending on your use case, it might be more appropriate to have an HDRI background, but they offer different benefits. The benefit of the physical sun sky being that you can configure the elevation of the sun, and if you're doing a strictly exterior scene, I think it'd be more appropriate to use the physical sun sky block here. There's some normalized parameters here, and in general, if you see any min and max range, this range will be sampled uniformly at runtime. So as part of defining your domain, you're generally going to want to, if let's say you're doing a, evening image, you might have the elevation much lower for the sun, but at runtime, each of these values, each of these ranges will be sampled randomly. So I could have a value between 0.1 and 0.5 for the sun's strength, which is a multiplier, 1 being full strength, and the sun rotation, it's the rotation about the vertical axis. Elevation being the angle of inclination with respect to the horizon. And if you're interested, you can select a specific sun sky model, either Nishida or the Hosek-Wilke algorithms or simulated sun skies. So that's the beginning of the scene. And again, at this point, we've only loaded in our base scene, which has the ground plane and surrounding terrain, and then our sun sky. So we have a base environment, including some geometry and the lighting. Next in the simulation, we'll be using our relationship editor, which I'll show here soon. And the relationship editor is a means of defining parametric relationships between multiple objects. So rather than loading objects in specific locations or having a pre-made asset, you're able to say, oh, well, I want, what if I want to distribute this certain object across the surface of another object with, these general bounds? That's how we would do that. So switch to the relationship editor here. And this is another relationship workflow block. This is specifically for relationships, which you can save to your account and reference throughout multiple simulations. Now, this is a basic, the general layout of a relationship is a parent and child relationship between two objects. So the parent object being what I've defined here is a ground plane. The ground plane is an object that exists in that preloaded scene, the land scene parking placement. That's an object that exists there. And then I'm populating that ground plane with a child object, in this case, person, is the category override I have for that. And it's retrieved from this collection in my scene. I'm sampling this collection between 8 and 12 times. So the placement system will go through this particular placement object and sample 8 to 12 unique assets from this collection. And then as part of this child object, you have a set of placement rules. So you're loading this object here from this people standing collection, and then you're applying these rules to said object with relationship to the in relation to the parent here. So I'm using different rules, a put rule, which places one object on another, and then a rotate rule, which rotates it about the different axis. It creates a rotation Euler. And again, we have documentation for all of these different components. So there's a quite extensive documentation specifically for the relationship editor, but also any other components you have in your simulation editor. So for example, again, here's that parent object that I referenced, as well as the child object, and then the set of placement rules. There are categorized into two different categories: basic transformations and complex transformations. basic transformations being translation, rotation, scaling, very simple defined transformations, and then the complex transformations being more, I guess, multi-relational transformations. So for example, the put object, it's not necessarily it's not strictly a translation, but it does employ multiple different sequences of transformations to do that. So again, the way this is quite a simple placement operation, but it's essentially just populating a ground plane, which is defined here, with people between 8 and 12 of them. So what I would do after this is I can save this set of placement rules and then reference those again after doing that in my simulation editor in the load relationships block here in our workflow. So at this point, again, we've loaded in our parking lot scene. We've added a sun and sky, and then we've loaded in the object relationships, which loads in people. So thus far, we don't have any vehicles in the scene yet, but we'll get to that in a bit. Next up is the camera. Every scene needs a camera. So even if you have geometry, you need to define, well, how am I going to capture an image of that? The camera we're using here is a perspectival camera, but we do have the option to use fisheye cameras if you have some sort of maybe a security camera, wide angle lens with some fisheye distortion. I'm referencing a curve in the scene, drone_area.curve, and that will be the initial placement of my camera. Curve parameter, it's from 0 to 1, where along that curve I will place the camera. And then there's some ranges for yaw, pitch, and roll for the camera, as well as camera height. And then in properties, you have the field of view. This is the horizontal field of view in radians of the lens. I'll note that while most simulations will use, you would define their the camera height and rotation here. We will be overriding this later, so these are sort of initialized with default values, and the values here for yaw, pitch, roll, and height will be overridden by one of our other blocks here. But in most simulations, you would define all of your camera intrinsics and extrinsics in the camera block. So after we've added in our camera, we can load in the vehicles into the scene. Again, we're using a collection to reference the objects, and if you would like to add your own 3D content into your simulation, you can create a blend file and upload them through our 3D assets tab here. You can create a new collection. Let's say you're, have a collection of, sedans. You could say vehicle_sedan. Drag your blend files into here, and then you'll be able to upload them to your account, and that would appear in your simulation editor under your collections. So in this case, I'm loading many different cars sampled between 3 and 5 onto a curve, road.curve. Again, this is a curve referenced in my scene. And I'm not applying random rotation, but that is an option. And then animation frames. So this is to produce a sequence of images. In a simulation such as maybe a highway scene where the cars are moving along the road, this would move the cars along the road.curve object in the scene. In this case, it's just placing them in the parking lot. But I am creating a sequence of 3 images. You could do 100 images if you want, but that would create simulating a drone path. The actual path of the camera then is overridden here by the track camera to object block, which I'll put here. So this is taking, it's referencing the an object called categorized by vehicle, and it's then tracking that object throughout the sequence of frames. So the reason that we're not the reason that we're doing it in this part of the simulation is because before then we had not referenced any cars, and if we were to put this before we load in any cars, it would not be able to track any objects, because at that point in the simulation there are no cars loaded in and it wouldn't be able to find the objects. So we're doing this only after we've actually loaded in the content. Just going into more of the parameters for this particular block. Again, we do have full documentation for all of these as well as examples. This track camera to object block will point the camera at an object that you specify, either by the object name or by the category property. And then you can vary the actual tracking point. So if you'd like, you can track the objects perfectly with no deviation from the center of the object. But we find, as a means to simulate some more like real world data where you're not going to be perfectly tracking an object, you can add in some noise into that camera path. So, for example, this is the tracking deviation curve that I'm displaying from within Blender, and you're able to define some bounds of that curve. So there are a number of control points. How complex you want this curve to be. The curve min and max values. So that would be the two-dimensional bounds. In this case, I have it plus or minus 15 meters. Obviously, you can tighten that to a smaller value if you'd like some tighter tracking of the object. But here I'm just to get some more varied images, I'm increasing that range quite a bit. Distance between points. These are just very specific to that curve that we're creating, and then the number of final points, the final complexity of that curve is defined here. So apart from the tracking curve, we have the actual camera path. So there's two parts to this block. It's essentially a track that the camera follows. So it's in this case, it's an elliptical orbit. So that's the actual position of the camera, and then you have the curve that the camera follows, which is roughly aligned to the target object. So in this case, I'm producing an elliptical orbit, but we have some other options such as being able to track the object or track the motion of the object directly. So like mimic the object's path of motion. So like follow it directly. Let me see, actually, manipulators, camera. I have match target. That's one of them. A linear path or elliptical. Linear path is just two points, follows a line directly, and then and tracks the object from there. So in this case, I'm doing an elliptical orbit, or it could be circular if you have the same radius. And that's how, again, and this is overriding the previous, anything that was defined previously in this camera block here is overridden by this block here. Let me see. So at this point now we have we've loaded in our scene, we've added our lighting, loaded in people using the relationships, loaded in the initial camera, including its field of view with for the camera intrinsics, as well as loading in the vehicles now. And then after we've loaded in the vehicles, we then modify the camera's rotation and position to track those objects in the scene. And then finally, we'll add some vegetation using a particle system. So every time the pipeline runs, it will create a new distribution of particles, or any sort of range you have defined here. It'll sample a new value. So this is how you define your domain. You have a minimum value and a maximum value, and then all of your data will be random combinations of those min-max values. So we can add in trees and bushes, again, using particle systems. Because these are instance particles, you can have hundreds or thousands of them and not worry about any performance issues. I do realize we are getting a little short on time, so I'll speed it up. And then after we've loaded in all of our content, we then get to our render passes. So the RGB image, that's our primary image that we're creating, as well as some compositing effects. So we can simulate some visual effects such as chromatic aberration or maybe some slight defocusing. And then finally, output our annotations. Default annotations are COCO format, so common objects in context. And you can check a box here to visualize those, which will create just a visualization of the images, but you can obviously visualize them yourself if that's more appropriate. And then finally, the actual image properties, so the resolution and number of samples. This is your final resolution of the output images. And then the ray trace samples is the samples per pixel of the ray tracer. So higher number of samples leads to a clearer image, but also takes longer to render. So 32 samples for an exterior image is perfectly appropriate, runs at a reasonable amount of time. And then we have several different image formats you can output in: PNG, TIFF, JPEG, as well as some bit depths for those, and RGB panchromatic if you're interested in changing the actual colors of the image. So after you have compiled your workflow, you can submit your simulation, specifying the number of data points. Let's say I want to do, I don't know, 600, and you can also distribute your data, your simulations across a number of compute nodes. I'll just do one for this example. Automatically start, I can check that, which will queue my simulation, which I can submit. And you will find in your simulation manager, see that it's queued and it just started. And that is my submitted simulation. Sorry for the increased speed at the end there, but I have gotten through everything, so can pass it off now.
Awesome. Thank you so much for the presentation. I already have a handful of questions for you guys. So first question is how do your simulations differ from NVIDIA OpenUSD assets and Omniverse simulations? And are your assets compatible with NVIDIA systems?
So my understanding of those assets is their USD format, which we do support. So we can use Omniverse assets. I think one of the primary differences is that our system's a little bit more managed. It's been a while since we've used the Omniverse system for synthetic data production. We have used it for kind of refining assets and for kind of 3D workflows. But yeah, my understanding as well is like the kind of various sensor modalities are not available at this time in Omniverse. But yeah, they're definitely doing a lot of work on the kind of 3D asset curation front, and I think they have some procedural tools now as well.
Awesome. Fantastic. Thank you. Another question, how do you program in the physical laws?
Physical laws meaning like gravity, things like that?
I'm assuming so, yes.
Yeah, all right. Those are Yeah, so I guess it depends on where those live. They could be done by the simulator, for example. In the case of like our space platform, like Spacehaven, we have an extra sort of executable in the tool chain that will model like orbital mechanics. So yeah, it's 90% of the time that's taken up by the simulation technology we're using.
Awesome. And then we've got another question for now. Do you have any classes or assets made for medical anatomy?
We don't right now. That would be kind of a special project, but happy to talk about it.
Okay, awesome. Again, thank you for everyone attending. If you have any questions, please feel free to put them into the Q&A tool here on Zoom. We are doing pretty good on time, so we've got little bit of time left for some more questions if anyone has any. But in the meantime, Francis and Christian, thank you both for coming to give this presentation. Again, this is being recorded, and so the recording will be available on the Nair Pilot YouTube channel in about a week or so, and will be available for viewing and sharing in that way. We do have for our attendees, I will post in the chat, we have a post-webinar survey. So if you're interested in giving some feedback, telling us how we did, what you'd like to see in the future as well, please feel free to fill that out. It's only about 2 minutes for the survey. And yeah, if there are no more questions, I do believe we are good there. So perfect. Okay, well, thank you both again. It was a fantastic presentation. And to our attendees, thank you all for joining us. And please keep an eye out on your emails and the events and trainings pages for future webinars. Thank you, everyone, and have a great day.
Thank you. Bye-bye.
Bye.
Thanks.